All right, welcome everybody. If you know Fred Lamb, you know that I am not Fred Lamb. I'm Dylan Spalding. I'm a senior scientist in Global Security Program at the Union of Concerned Scientists, and I'm on the program committee for the Forum on Physics and Society, which organized this session. Dr. Lamb unfortunately was unable to attend at the last minute, so I'm stepping in to chair in his stead. So this session is jointly sponsored as well with the Forum on International Physics. And I definitely want to give Dr. Lamb credit for organizing the session. So before we begin, I'd like to remind you quickly that the Forum on Physics and Society has several more sessions over the course of the conference. On Thursday, tomorrow, we have session G1, which is on small modular reactors and climate change, with Secretary of Energy Steve Chu as one of the speakers. That'll be in ballroom A1. We also have our award session tomorrow, which will honor Galileo Violini and Robert Budnitz with the Burton and Szilard Awards from the Forum, as well as invited speaker Kartik Sheth from NASA. That'll be in this room. And finally, on Friday, we have another session related to the role of physicists in arms control, if this session tickles your fancy. That session will be run as a panel discussion with Stephen Schwartz, Lisbeth Gronlund, and Raymond Johnlow also in this room Friday morning at 10:30. So today's session features speakers who spoke at a workshop that was held last October at the International Center for Theoretical Physics in Trieste, Italy. The workshop was co-sponsored by the Physicists Coalition for Nuclear Threat Reduction, which is an exhibitor at this meeting, if you want more information, as well as the APS Forum on Physics and Society, and it convened approximately 45 physicists from 15 nations, focused on the question of how can physicists help reduce the nuclear threat. So each of our speakers today has half an hour to speak, and hopefully we'll have time for some questions. And our first speaker is Dr. Lindsay Rand. Lindsay is currently a postdoc at Stanford University Center for International Security and Cooperation. Her research focuses on socio-technical issues at the intersection of science and international security, especially in nuclear and quantum technologies. She's an expert on the technical aspects of the control and verification of nuclear and emerging arms technology. She has a Bachelor of Arts in Physics and Classical Studies from Carleton and an MS in Nuclear Health Physics from Georgetown, a master's degree in Public Policy and PhD in International and Security Studies from University of Maryland. And she's been a research associate in the Center for Global Security Research at Lawrence Livermore, as well as a Stanton Nuclear Security Fellow at the Carnegie Endowment for International Peace. So I will step aside and let Lindsay begin her talk.
Okay, so one area that is kind of becoming a hotspot in nuclear policy right now is the impact of emerging technologies. So I want to talk about this because I think that is an area where physicists have a lot to contribute in informing the discussion for how to make force structure decisions or engage in arms control when there is uncertainty about technologies that are emerging. So I focus on quantum technologies, which is a very broad category, but is gaining a lot of policymaker interest. So what I try to do is kind of drill down into specific areas of quantum technologies and translate that to strategic impact. So I'm just going to go over, some of the social and policy forces behind this whole second quantum revolution hype right now, and give a very high-level overview of, the R&D that's kind of making policymakers interested in quantum technologies. And then where I see the major implications for quantum technologies on nuclear deterrence, and particularly risk areas. And then how to bring in technical analyses to improve policy and governance, and specifically what can physicists do. So I'm sure everyone's been seeing and hearing at this conference, but obviously quantum technologies are in the headlines right now, and a lot of people beyond physics are actually becoming interested in quantum. And so, you saw that 2022 Nobel Prize go to a trio of physicists working on photon entanglement. And actually in 2023, some chemists also won for quantum dots, which isn't necessarily have to do with quantum information science because part of the rationale is for their energy applications, but inevitably policymakers are roping this into the whole quantum computing drive. This is substantiated by surge in publications, specifically on quantum computing and quantum sensing and quantum communication. This is just quantum computing, but you're beginning to see people citing these higher level technologies rather than the smaller research areas that people used to be citing, and they still are, but now they're lumping them under like quantum computing. There's also a massive amount of funding. So you see funding from the private sector, like the left-hand figure shows, and actually from governments as well. So a major uptick in funding from the US government, but this is also occurring globally. So from Japan, UK, Canada, China, these countries are seeing the largest rise, but all other countries are also having government investment in quantum technologies. And I think what's really telling of the fact that some of this basic R&D is transitioning to more technology or potentially even application-ready technologies is the surge in patents that has been occurring, a pretty big uptick starting in 2013. So I don't know if anybody's heard the term, but a lot of people in the policy sphere are using the term second quantum revolution. When I first heard quantum technology, I thought it was kind of a funny term because I feel like physicists would say, well, everything uses quantum, or quite a few things. And when I drilled down, I think this all comes from a 2002 article that really starts to say that no, the second quantum revolution is defined by the ability to measure individual quantum systems, whereas previous technologies that were adapting quantum capabilities were actually looking at quantum systems in the aggregate. And so this is really based around the idea of qubits, or singular quantum objects that store information and can be manipulated with quantum techniques. They're somewhat analogous to binary bits in classical computing. So the idea is that you have a two-level system. Obviously, with the Hilbert space, you could have a much higher dimensional space, but right now it's largely focused on two-dimensional, although there are proposals to do quantum information systems with higher level dimensions, and those would be called qubits with a D. But actually, we're really constrained to qubits right now because of some of the math, and how we understand computing comes from our knowledge of classical computing. And so if you are looking at this and you're like, well, can't most things that at the quantum level be a qubit? The answer is yes, and that is contributing to a lot of the confusion around quantum systems because there's such a wide variety of qubit options. And yeah, so just to show, I mean, yes, physicists know a lot of things used quantum way before the qubit arose, but right now people are talking about quantum computing and communication and sensing based on these individual quantum systems. So when you're looking at the technology level rather than the individual smaller research focus level, it can be difficult to map the higher level trends. Typically, quantum technologies are broken out into three types, which are enormous branches in and of themselves. So you've got quantum computing, quantum communication, quantum sensing, and simulation normally rolls in with quantum computing, but it can also be its own thing. But actually, despite the fact that policymakers want you to focus on each of these areas, they each actually have underlying research in physics, chemistry, material science, computer science, math, and engineering. So they're really not super narrow levels. And then beyond that, within each of those types of quantum platforms, you can have the variety of qubit systems as your base for analysis. And because there's such a wide variety of things that can operate as qubits, but maybe in like 10 years ago even, this was a source of competition between research groups. I was at University of Maryland, so it definitely was there. But like which type of qubit was going to work the best. I think within the past maybe even 2 or 3 years, it's become more recognized that each type of qubit will have its own unique strengths and weaknesses, which means you're going to be moving towards hybrid platforms. So you'll have some qubits performing certain functions and others not. But so that adds to the complexity of translating all of the R&D to policymakers. And so you're beginning to see this surge in research around the 2000s, largely aided by some of the improvements in methods and techniques in physics, such as cryogenic capabilities, higher sensitivity lasers, as well as material synthesis, and also just the sheer amount of funding and personnel and interested PhD students has significantly rose, even since I was an undergrad. But it's very, very difficult, as I've been saying, to communicate to policymakers because each of these technologies is also in a different phase of development, and it's actually very application specific too, whether or not you're close to getting a useful technology. Some notable improvements that have given policymakers hope or that scientists have communicated as major benefits is we have much better characterization of qubits or quantum materials. So this allows us to have greater certainty in some of our readout techniques, better techniques and lab setups for manipulating and measuring qubits, and significant work to improve the math and theory to allow us to operate under more technical constraints and kind of circumvent some of the issues we're seeing in lab setups. But what I always try to point out to policymakers when I talk about this with them is there are still inherent obstacles that we're addressing. So part of the issue with quantum systems is that because qubits are susceptible to environmental perturbation, which can allow them to entangle and get you the quantum benefit, that also means they suffer decoherence compared to certain things. So the more you shield your system to decoherence, or the type of qubit you select that is less prone to decoherence, the harder it is to manipulate it in the way that you have high certainty in how it's functioning. So this is just an inherent trade-off that we'll have to work around in the quantum field. Entanglement schemes are still very difficult beyond the lab setting, so especially in operational environments. If you've never had to operate a laser table, this is something that I feel like a lot of policymakers just can't really understand just how difficult it is. And then the inherent issue is scaling to more qubits because of that entanglement challenge, which is where you actually see a lot of the theoretical gain is when you begin to scale up, either to higher numbers of qubits in a processor or in a network. But if you're constrained by your entanglement schemes, then you can't really begin to see that scaling benefit yet. And then you'll need to be able to come up with error correction systems. So I always try to point these out to show that even if you're seeing the big research articles coming out, when you're thinking about transitioning to a functional technology, these are some of the issues I think are important. But because there's so much hype around quantum, there's still a benefit to trying to bound the uncertainty as much as possible. So this is an area where I think physicists and technical people can really contribute because we have a better idea of the constraints that these systems will face when they're innovating over time. And also, if we can think beyond the lab setting into operability conditions, we might be able to anticipate some of the issues that you could see that might not be apparent if you don't necessarily have a technical background. So I'm going to just go through what the main implications that have been proposed for each of the different technology areas, and then I'll give my assessment of whether I think they will be impactful for nuclear deterrence or what the impact would be, and then I'll go through an example of a technical analysis I did. So for quantum computing, the premise is that you would place these qubits into superposition states and theoretically be able to parallel process a lot of different configurations for the qubits or in a bit setup and then run your full solution set at once. The promise, if you are able to scale up to a multiple qubit system, is that because you're parallel processing all the possible configurations, this number is thrown around a lot. You could speed up to a 2n value and be able to solve combinatorial problems with large solution spaces. However, what I think the major caveats are that get lost when people are projecting these theoretical gains is the fact that as we've seen them being developed, these processors are not going to be super accessible for large data volumes. Actually, they're going to be better for handling data that's packaged into patterns. And they're also not going to be super flexible very quickly. So you can't kind of plug in whatever data you have and then rapidly have a solution. It will take time to reconfigure the processor. Also, what people don't understand is that the readout for a quantum computer is stochastic. So unlike a traditional computer, it's not that you run through the process and then get your answer, which is a deterministic answer. Because it's stochastic, you'll have to run it 10 to 100 to maybe more times. So you're never actually even going to saturate that 2 to the n level because of the number of times you're going to have to run your process. Nevertheless, I mean, one area that I do think quantum computing could be impactful for deterrence is if you could decrypt your adversary's communications. So because people are proposing this as an application, it's introducing a lot of concern about the robustness of the intelligence that you need to run your command and control for a nuclear system. I think one option that people have also proposed is using it for system optimization, either to track various delivery vehicles or to get better surveillance over your adversary's force movements. However, because I pointed out, I don't think that in the near term you're going to see processors that are easily adaptable very quickly. And the time sensitivity required for systems optimization, I don't think that this is going to be an area of major concern. But I do think one area is the materials R&D. So because quantum simulation can already be used in lab settings, just simulating the quantum computer, but at slower speeds. This is something that you could begin to see improvements for like stealth technology or stealth materials. We might be able to see it replace traditional methods for testing nuclear weapons, which would be great because then we can avoid having to test nuclear weapons again. And other second order implications, but these are very hard to anticipate because they're occurring in the lab. So I think these are very skeptical, but theoretically those could be areas where you see some implications. Quantum communication is the next area that has been getting quite a bit of funding from the Air Force and the Army. The premise here is that you would leverage entanglement schemes to ensure the security of your information transmission. And because of the quantum measurement phenomena, where when you measure a system, the wave function collapses, the idea is that if an adversary tried to interfere into your communication, not only would the system collapse, so they could not receive the information, but you would have some level of awareness that somebody had been trying to intercept your message. This is typically referred to QKD, although there's a few different configurations for how this might work. The issue with this is entanglement is very challenging in operational settings, and the entanglement schemes can decohere over distances. And whereas in a traditional communication platform, you use repeaters, which take your signal, then read it, and then amplify it and send it over a further distance so you can extend your distance beyond what the original signal would have traveled. Because of the measurement phenomena, quantum repeaters are very difficult, and recently there have actually been a few proposals within the past year or two, but we're still trying to figure out how that would even work. So, it's a very challenging workaround to try and repeat a quantum signal and send it over a further distance. But on the implication side, I guess if you could come up with a quantum communication system, I don't think it would be inherently destabilizing. I think it could be stabilizing because you could ensure your confidence in the security of your information. So I don't view it as, I also think this figure is kind of crazy, but this is one of the reasons why we need more people going into here, because otherwise policymakers will come up with this sort of figure. Although I will say one very interesting application of quantum communication would be in communicating with submarines. So submarines they're survivable second strike. That means that they provide reassurance that your deterrence is working and some sense of strategic stability because they're constantly hidden underwater. However, when they have to get communication from the command center, they need to surface. And in order to surface, when they surface, they expose themselves to either tracking and detection from an adversary or even attack. So if you could use entanglement to communicate underwater better, then you might be able to increase the invulnerability of your submarine, which should stabilize your deterrence balance, but I think this is pretty speculative too. The biggest impact I foresee is with quantum sensing, which is kind of I mean, it's kind of a strange term because it's a pretty ubiquitous process, but it's the idea of using qubits to actually take what is a disadvantage in quantum computing and quantum communication, which is the susceptibility to environmental perturbation, and you actually say, okay, well, I will measure how it is impacted by the environmental perturbation and use that to measure the perturbation. So then you can measure electric fields, and magnetic fields, and gravitational fields, acceleration, a lot of different things with your qubit. The caveat is, qubits respond to a lot of different things, so you have to make sure it's a highly characterized setup where you know it's only responding to this type of measurement or the type of signal that you are trying to measure. But we have seen a lot of progress in lab settings, particularly at University of Maryland, but I'm sure other places. We get a lot at UMD. The issue is when people are proposing to policymakers the types of gains you would get from a quantum sensing system in this detection sensitivity, they're often referring to entangled networks, and that is not where we have seen operability outside of the lab. So if we could get these improved quantum sensors, this is where I think the biggest implications would be. So you could improve the timing to synchronize your command and control. Again, this probably just adds a little bit more stability for your communications. But where the really disruptive areas would increasing missile accuracy. So improving missile accuracy through using position navigation and timing capabilities with quantum sensors like inertial guidance. This could make countries very concerned about the survivability of their nuclear arsenals and potentially incentivize an arms race. So this is something I'm very concerned about. Likewise, using quantum sensors to detect nuclear submarines and to monitor mobile missile travel. And so if countries believe that these second strike capabilities can be tracked, they are less likely to want to engage in arms control and probably more likely to want to build up their nuclear arsenals. So when I have met with people in the government, because this was what my dissertation was about, a lot of them said that this is one of the reasons, not quantum sensors specifically, but increased accuracy for detection and tracking is one of the reasons why they want to reinforce nuclear arsenals and build up more capabilities. So what I wanted to do then is figure out, okay, is there some way I can actually anticipate whether this is actually going to be impactful or if this is them all just blowing smoke? So the issue with working on nuclear weapons is that a lot of the information is classified, but luckily physics can work around a lot of that if you make some assumptions. So I just used a magnetic field perturbation calculation and used assumptions about what submarine parameters are, so the makeup of the hull and the dimensions of the hull to calculate the perturbation it makes in the local magnetic field. And then using a signal strength assumption, I calculate how far that signal would propagate, and then I set that equal to the lowest, the smallest degree of difference you could measure with each of the sensors based on sensitivities that have been achieved in the lab, which is a huge assumption because assuming the sensitivities achieved in lab could be achieved in an operational setting is high. But if I'm trying to show that even at their best, quantum sensors won't make submarines detectable, then I'm fine taking the upper calculation. So that's why I use those lab sensitivities. And then if you look at the chart, there's two important things. One is that the two sensors on the upper left-hand side, which have the better sensitivity because you want the smaller value, that's your smaller degree of difference you're measuring, are actually not new. So those are the old sensors we've had since the 50s and 60s. Surfs and squids are not fundamentally new quantum sensors like everybody's talking about. And also, when you look at the y-axis, so that's 10,000 to 15,000 meters, which might seem far if you're thinking about running. But if you're thinking about the vastness of the ocean, you would need hundreds of thousands or millions of sensors. So that's where physicists can just kind of step out of the lab and try to think about the operability. We can really provide a lot of value add to these calculations. Because with them, what I showed is if you took those distances, even for the old sensors, which are at the highest sensitivity right now, you would need a huge network of buoys, which would itself be a security issue because you're kind of indicating you're trying to track all their submarines. And then even if you were like, okay, well, I don't need to track the whole ocean, I will perform persistent tracking. I did some Bayesian analysis to track or to figure out how many you would need and how long it would take. And essentially, the real constraint is the battery life for drones and the speed at which submarines move, so the drones would have to match that. It's not super feasible, and it's possible you would lose the submarine a lot more easily than if you had the whole ocean network. Furthermore, countermeasures are almost always cheaper and easier to develop than the actual measure. So you could imagine improvements to stealth capabilities, which silence the signature from the sub. So that's the figure on the right, showing how that would decrease your distance for detection. And we've already seen a significant increase in stealth capabilities. So as I talked about with the materials R&D, you might even see a further decrease in signal. But also there's really cheap workarounds. So you could come up with ways to spoof with decoys or jam with pulse emitters, or even just to interfere with the network. You could program a drone to take out some of these buoys, and then that's that. So I think, the countermeasures are always, you can always come up with ways to work around some of the issues too. So I find, I don't think any of this shows there's reason to believe submarines would become invulnerable, and therefore we don't have to base our force structure decisions around that concern. I did a similar analysis for missile accuracy. The idea being that if a country could improve its missile accuracy, then your ICBMs might be more susceptible to attack, and specifically with lower yield nuclear warheads or even conventional warheads, which could, create crisis escalation scenarios or even arms racing buildup. Missile accuracy uses this very weird term called circular error probable. It's just the radius at which the missile is likely, the missile will fall within the radius 50% of the time. I don't know why they came up with circular error probable, but that's the missile accuracy estimate. And if you look at the CEPs, since missiles have been developed in the 1960s, they have gradually decreased. Actually went through a pretty substantial decrease with inertial navigation and computers in the 70s. But they're hovering right around 100 to 200 meters, and you would really need it to get down to 10 meters or less to do a very low yield or conventional attack. So I looked at the contributions to missile accuracy and went through all the work of trying to figure out where quantum sensors would potentially improve your accuracy. But then I just looked at the sensitivities again, and once again, the quantum sensors are not outperforming the traditional sensors, which in this case are the sensors on the bottom, the ring laser gyro, and the MEMS. I think the value add for quantum sensors is that they would be decreased size or swap parameters, size, weight, and power eventually, so you might be able to put them on the missile the missile warhead reentry vehicle, which means you could readjust in the reentry phase, but obviously in reentry through the atmosphere has a very high likelihood of disrupting the quantum platform because they're so sensitive, so I think that's very speculative to assume that you'd be able to operate with that. Furthermore, if you were to lower your warhead yield or use conventional warheads, we don't really know the physics very well for the likelihood that that would destroy a silo, so I wouldn't start to build up silos because of this concern. There's also, you could just use decoy silos to decrease the likelihood that they'd be able to attack all of your silos without actually having to fill them with warheads. You could offset with point missile defense, or use grates or pebble beds to just redistribute the impact. Even a significant or a slight redistribution with conventional or low yield could be impactful. So what do I think the value is of even like these technical analysis that we might feel uncomfortable with because there's a lot of uncertainty? I think they show that yes, more progress is likely, but there's still significant experimental and operational hurdles that you can expect. And I just hope that it can at least shed enough doubt in people's minds to abate these concerns about a technological surprise and submarines all of a sudden becoming vulnerable. I think they also show there's a lot of continuity. It's probably intuitive to physicists, but not to policymakers, that technologies don't just come out of nowhere. Oftentimes you have these older capabilities that operate with some degree of accuracy, and you have the new ones, and they slowly start to supplant the old ones' sensitivities. And so I feel like I'm showing that it's more gradual than policymakers are expecting. And then just, regardless, I think there are ways policymakers can help to anticipate some of the uncertainty, and that's where, thinking about countermeasures can be useful because it can show easy workarounds that might not be intuitive to policymakers. Nevertheless, they are very interested in quantum technologies and putting all this funding into quantum technologies, and then at the same time worrying that nuclear deterrence might be disrupted by quantum technologies. So this is why it's important for us to engage in the dialogue. I want to make sure I have time for Q&A, but I have a couple of areas I propose for helping policymakers learn about quantum technologies, but I can go through those quickly. Just, being aware of the different types of platforms, coming up with clear metrics for when quantum is actually outperforming classical clearly seems to be a big issue, and so I think coming up with metrics for when they might know that a quantum is overtaking a classical technology or an existing technology would be helpful. And I think just, when we're writing in the technical journals, it's fine to only communicate experimental challenges, but when we are communicating with policymakers, we need to express the challenges beyond just the lab setting. So thinking about operational issues like those deployment schemes I showed, issues to scaling, so developing these technologies in large volumes, and then basic theoretical issues too. So I think communicating all of that can help them see the bigger picture, that when they see some article that says sensors are reaching this high sensitivity, it doesn't necessarily mean it's going to be a huge shift that we need to suddenly build up our nuclear arsenals because of, but there's all these issues that make it less likely to be disruptive. And then one issue that I did hear talking to policymakers is they are concerned about science communication trends. I guess there is a big push for promoting hype in science right now because of social media and venture capital actually. Venture capital is now funding some research groups and research programs, and that's creating incentives for scientists to hype up their findings without expressing the implications clearly. And so there is some journal evidence I found after this issue was raised, so I think this is something we could do to look inward and think about, yes, there's a time to promote our research, but also when we're talking to policymakers, we probably don't want to say, this is going to have this huge advantage if we're not really sure about that. So this is basically a summary of what I said. So just pushing for renewed technical assessment and oversight. So bodies in the government that can bring in technical people have actually been labeled as political, and so the Office of Technical Assessment, which was in Congress in the 90s during the Cold War, was canceled because it was perceived as too technical, and the Republican Party canceled it. So we probably want to make sure we can continue to get more technical assessments within the government, regardless of the politics. And then helping build a healthy communication, so addressing this science hype issue internally, and also kind of trying to bring the technical analysis to policymakers. So I'd be interested to hear if you guys think I'm off base, or if your experience working with policymakers on these issues, or any questions you have. Yeah, I stuck right out.
All right, we certainly have time for questions. If you can, please use the mic because these sessions will be recorded for viewers online later. So.
I have a question about your submarine calculation.
Mm-hmm.
So do you have any idea of what the background magnetic field in the ocean looks like that you'd be competing with there? And if you even were close enough to detect it, what would a submarine signal look like in that scenario?
Yes, so the background is worked into that when I solve the equation. It's one of those values. The issue is the background changes depending on the depth and where you are, and various weather factors as well. But the government has maps of the magnetic fields. So my idea is I took the worst case scenario magnetic fields, the highest background, which would require the biggest sensor signal because I'm trying to show the worst case scenario. But realistically, the government could take that equation and put in the different values. So I tried to go work around the variances by just going with worst case scenario, but yes, yeah.
Hi, so there are two types of policymakers that you deal with when you hear quantum. One you've already touched on is the one that gets really, really concerned really quickly about the implications, and the other goes the other direction, which is that, okay, we've had quantum tech promised to us for the past 25 years, so why should I care now? How do you working with the second type of person?
Yeah, I mean, that's true. So quantum, right now, the discussions are largely in QEDC, Quantum Economic Development Consortium, but I've talked with people in DoD, state, everywhere when I was in DC last year doing field research, and you're right, there are people comparing it to fusion, specifically quantum computing, and when I think about the risks, there's the risk that you are underprepared, or the risk that you're over-prepared. And if you're over-prepared, then you're sending a signal to other countries that we're building up this technology, and they might perceive that as escalatory. So there are benefits and risks to doing that. And likewise, there are benefits and risks to being underprepared, like you're saying. And definitely getting people to prepare for things that would be really, really bad, like post-quantum decryption, is normally what I focus on. But the issue is, even in the past 2 or 3 years, people are now required to fund post-quantum decryption even if they don't have a technical basis for it. So I think it's really more shifting towards people in the type 1 category anyway. But I mean, I think I just say, you can focus on the defensive measures. Like if you're really concerned about submarine detection, then focus on these really cheap countermeasures, or focus on post-quantum encryption capabilities, rather than necessarily building up these offensive capabilities or capabilities that could be perceived as offensive. But it's changed a lot over the past even 3 or 4 years. So with the congressional mandate, there's very few people who now don't at least partake in some quantum preparation.
Okay, thank you.
Any more questions? I guess I'll ask a brief one. So you mentioned, that incorporating some of these devices in warheads is challenging. Can you say a little bit more about how far away the hardware is to surviving the sort of launch to target sequence?
Yes. So right now we don't have re-entry navigation. So you are just basically going off the ballistic trajectory, which, we're physicists, so that should be detectable. But the issue is, once you go into re-entry, there's a lot of uncertainty added to your navigation budget. So that contributes to the CEP significantly. And the issue is right now we don't have guaranteed navigation past re-entry. We could put GPS signals on it so we could communicate with it, but because of the plasma buildup and the potential that an adversary could take out your satellite, people don't want to rely on GPS navigation. It's very unreliable. So that's where quantum, the value add is that quantum could allow for dead reckoning or navigation without external communications. But it has to survive re-entry and the plasma buildup. So this is definitely debated, but I think, there's a chance in maybe 10 or 20 years we could have high certainty in that, but I think that the issue is you're going to want to have a high degree of certainty that it would work, and I'm not really sure that would be possible in the near term. But Lockheed Martin and Boeing are testing it right now, so I guess theoretically they're working on it.
Right, any final questions? We'll move on to our next speaker.
Okay. I just wanted to quickly ask, because how does this play into deterrence? How is it not just, technology war or making a technology better army or equipped system? Because, deterrence usually comes with fear of the public of annihilation, and
Yes.
I mean, that is just kind of development of better weapons, isn't it?
Well, I mean, it depends on what you mean by better. So I think there's different thoughts about how deterrence works. Some people believe you just need a very minimal retaliatory capability. So just even having one or two, not one or two, but on the scale of like a handful of weapons that could survive a first strike, then that is how deterrence works. Then you can guarantee that you'd have a retaliatory capability. And that's where the submarines come in, and why the submarine calculation is so important, because if those submarines become vulnerable, then your deterrence value might go down, because people could be concerned that submarines could be taken out in a first strike. But then the political question becomes how many do you need to have an assured capability? And so that you don't answer through a physics equation. That's where you give them the data, and then that's the strategic community's role.
Great, thank you very much, Lindsay. So our second speaker today is Dr. Igor Moric. Igor is currently a postdoc at Princeton University in the program on science and global security. He's pursued innovative technology and policy approaches to support further nuclear arms reduction and the next generation of nuclear arms control. And his current research focuses on examining how overhead transparency provided by swarms of observational satellites can support nuclear nonproliferation and verification of compliance with treaty commitments, and how this affects nuclear stability in relationships of nuclear weapon states. Sorry for the mic here. Igor had a master's degree in physics from University of Zagreb, an advanced master's degree in space systems engineering from ISAE Supero in Toulouse, and a PhD in physics from Pierre and Marie Curie in Paris. And I will turn it over to Igor.
Okay. So I will speak about the current capabilities of Earth observation satellites, how we can expect they will evolve in the near future, how this may impact the relationship between nuclear weapon states. I don't know if you can hear me. It seems it's breaking. It's fine. It's based, the presentation is based on the two papers, which you can see on the top right. Oh. So I will start with a brief historical overview on how imaging satellites evolved during the Cold War and how they impacted the Cold War competition. So nuclear programs were shrouded in secrecy since their beginning. Since there was no way to verify what the other side was doing, and there was no trust, the only safe assumption was the worst case scenario. So the assumption that the other side is building as many weapons as possible and is preparing to strike at any point in time. So a quasi-balance was established, which was reinforced by the return of massive retaliatory power, which is the basis of the relationship of nuclear weapon states even today. And in line with this strategy in the 50s, the US and the Soviets continued to build nuclear weapons, believing this would be advantageous in a potential nuclear war. But with so many weapons available, soon came a realization that neither side's retaliatory weapons, they're both in danger from a surprise attack. So both sides needed enough time to prepare their forces and to ensure the nuclear deterrent. To figure out what the other side was doing, US expanded its human and communication capabilities. It introduced atmospheric sample collection, spy planes, and President Eisenhower proposed the Open Skies Treaty, which was declined by the Soviets at the time. All the information from this was not enough, it wasn't comprehensive enough, and the lack of intelligence led to the bomber gap and the missile gap. The bomber gap was the belief from the US that the Soviets had many more nuclear bombers than them, and the missile gap was a belief that the Soviets had much more advanced missile ballistic technology and more ballistic missiles. And again, this fear of the surprise attack and these mistaken beliefs further stimulated an increase in military spending and the buildup of weapons of both sides. In 1960, US started the Corona Space Surveillance Program, with the first satellite providing 13-meter optical resolution imagery. And the satellite used film and it returned the exposed film parachute with a recovery capsule, which was then grabbed in midair by an airplane, as shown here on the top right. So all this to obtain black and white imagery with a delay of days or even weeks. However, the capabilities were good enough to detect new construction of infrastructure and bases, and the imagery confirmed that the missile gap was actually real. But it shows that the Soviets had less weapons and the US had more weapons and was more advanced. In addition, it also showed a major deficiency of Soviet nuclear forces. So these findings limited the guessing of US war planners and led to the reduction of the number of US nuclear warheads. At the same time, imagery also revealed that the Soviets lacked a long-range delivery capability, which may have contributed to the Cuban Missile Crisis a few years later. So a few years after the Corona mission, the number of satellite missions increased and their capabilities improved. It became possible to detect and monitor construction as it happened, deployment of radars and ICBM complexes deep within the enemy's territory, as well as monitor the emerging nuclear programs of new nuclear weapon states. So in 1964, US observed the aftermath of the first Chinese nuclear test with 3-meter resolution, and only a few years later with sub-meter resolution, providing much more detail. So this was allowed, basically. The overflights of satellites were allowed because they did not enter the airspace. It was believed that they provide much less information than they actually, than spy planes, and it's also possible the decision makers did not fully understand the potential of this technology in the future. And the technology improved so much that by 1968, US defense agencies could make a claim that no new ICBM complexes were deployed in the Soviet Union in the past year, basing this claim solely on satellite imagery. The Cuban Missile Crisis and the growing visibility of arsenals seen from space made it clear that a preemptive attack was not feasible, that a nuclear war cannot have winners. Therefore, if winning is not possible, a stalemate needed to be established, maintained, and it had to be certain and indefinite. In the 70s, the US and the Soviets agreed on various arms control treaties, which were aimed at managing their competition, controlling the nuclear testing, controlling deployment and development of disruptive offensive and defensive arms. So it's important to note here that the development of satellites, of technology, did not drive the political decisions to lead to arms control. But the technology facilitated arms control once the political environment aligned. And it made, overall, the increase in transparency stabilize the relationship between the US and the Soviet Union and made everyone safer. So there isn't much time to go into what happened since then, but I will say that the technology significantly improved, as did the US understanding of Russian forces. In the meantime, we also had the emergence of commercial imagery. So basically, private companies which launch satellites and offer imagery to the public and to the governments. And because of miniaturization of technology, cheaper launches, today we have hundreds of these commercial satellites imaging in high resolution, allowing us to detect and monitor objects the size of a human, essentially. So the bottom image was produced by a US spy satellite, KH-11, with a 10-centimeter resolution, and it shows a failed Iranian missile launch in 2019. The top left image was produced by a US company called Maxar with 30-centimeter resolution, which they claim is equivalent to 15. And you can see that in this scene, you can see individual vehicles and even humans if you zoom in. The image on the top right is impressive because it's 30-centimeter resolution. It shows an aftermath of a missile strike in Ukraine. And it's impressive because it was taken from the side, and you can actually see individual windows and the full extent of the damage. Today, we also see more bands, more beyond what's possible with a human eye. These are images from synthetic aperture radar, which provides visibility during night and through clouds. It is especially useful for detecting human-made and metallic objects, but also making these 3D maps of the surface, as you can see on the top left. And since the atmosphere does not affect the viewing of the sensor, it's also very useful for change detection, as you can see on the bottom left. So you can image from the same location and the clouds or light do not affect it. And what you can see here is daily frequency of a harbor, and these are oil silos, and you can see how they move based on the amount of oil in the silos. The bottom right image shows preparation for a Russian missile test at a location which was not possible to observe before because of persistent cloud coverage. We have other bands. So the top row shows in order shortwave, midwave, and longwave infrared. Infrared is especially useful because you can see thermal outputs, which are indicative of human activity. So the top left image shows fighting in Gaza. The middle image shows a city during night, while the image on the top right shows a nuclear facility in North Korea, where these red spots indicate higher temperature and higher activity, which is especially useful in North Korea because ground inspectors do not have ground access. The bottom row shows hyperspectral imagery. So hyperspectral sensors probe the electromagnetic spectrum, and they can provide a level of material classification. So as solar radiation bounces off ground targets, it carries some information on the chemical composition or whatever it bounces off. So the bottom right image is relatively low resolution, 30-meter hyperspectral imagery, which allows you to see different types, to classify different types of soil and ground. While the bottom left image is 8-meter hyperspectral, and it shows detection of gas leaks from a gas pipeline, something which is not possible to observe with visible optical sensors. Finally, maybe most importantly, because of improvement of technology, the satellites are much smaller. We can launch more of them, which means better coverage, so higher frequency observation. This slide shows an explosion in the number of launches in the past few years, and at the same time, mass is decreasing. So just to illustrate this, on the bottom you see the Corona satellite, so the first one, which I've talked about before, which had a resolution of 13 meters, and it's basically the size of a van, while these new satellites launched by a US company called Planet, which have a resolution of 4 meters, basically fit in one hand. So this is maybe the most important advancement of remote sensing of overhead satellites. It allows for a much better monitoring of ground activity and change detection. So the top example shows before and after of a flood event in Libya in 2023 as taken by those Planet small satellites. The bottom image is again SAR, showing daily frequency imagery of another harbor, showing how ships are leaving and entering. It also allows you to see trucks taking the cargo, and even personal vehicles as the parking fluctuates per day. Having a higher frequency observation means also a higher probability of capturing rare events. This is a Chinese submarine entering an underground base, and was captured by those small Planet satellites in 2020. So while before, during the Cold War, it might have been possible to observe locations maybe once per month if cloud coverage allowed. Today, if we combine all the commercial satellites into one super constellation, it becomes possible to observe the Northern Hemisphere on average once per day with 5-meter resolution and maybe every few hours with SAR. So this is a simulation I made taking into account all the commercial companies which offer imagery to the public. And it takes into account a statistical average of cloud coverage based on 30-year history. So again, this is only considering commercial satellites. If we also include the spy or national satellites, the frequency will further increase. Using the same simulation, I looked at the territory of China, and I excluded the Chinese companies. And the simulation shows that it's possible to monitor the location of newly discovered ICBM silos with a frequency of every 2 to 3 hours with 5-meter optical, and every 1 hour with SAR. So this is a resolution which allows not only detection of silos, but also detection of possible uploading of missiles. So these are all new capabilities which were not available in the Cold War. So that's what exists now. This slide kind of tries to show what we can expect in the near future. So US defense agencies are launching and developing a number of constellations in the optical, in SAR, to monitor moving targets. They are launching a next generation of early warning systems, and the Space Development Agency is also launching a few hundred LEO-based satellites to monitor hypersonic and ICBM launches. And also there was recent news that Starlink is developing spy observation constellation for the US government, just last week, I think. On the commercial side, all the big companies, Airbus, Maxar, Planet, are either expanding their existing constellations or launching new ones with a resolution of under 30 centimeter. There's a bunch of companies outside of the US and Europe also deploying satellites, such as the Argentinian SatLogic, which is deploying a large constellation of sub-meter resolution, optical resolution satellites, the Finnish ISI, which is a SAR provider, and of course China is deploying a number of dual-use civilian military systems which are imaging in different bands. And there are also recent news that China launched in December, I think, geo-based optical satellite, which allegedly has a resolution of 2.5 meter and can allegedly provide persistent coverage of the Indo-Pacific. Of course, if there's no cloud coverage and during day. There's also some emerging capabilities provided by commercial companies. So I've already shown the 8-meter hyperspectral, which is being taken by a US company called Orbital Sidekick. There's also a US company called Albedo, which was recently licensed to image in the 10-centimeter region, which is equivalent to aerial imagery. There's also an emergence of companies which are offering a radio frequency sensors in orbit, which can detect radio emissions and the use of radar. So the example on the right is from Hawkeye 360. It shows at the bottom Chinese ships in the South China Sea using the transponder, and on the top it's the same scene with the ships which are not using the transponder but were detected by radio transmissions. Okay, so there's a lot of data being produced by different sensors from different angles and different bands. It's increasingly more difficult for human analysts to manually fuse the data, process, and analyze it. So the emergence of sensing capabilities is linked to the emergence of AI and algorithms which are able to do this automatically, much faster than humans. And this includes automated detection, classification, and tracking. And this animation was taken from a much longer video from a company which uses optical imagery and then applies their algorithms to detect, classify, and even track vehicles in urban and non-urban environment. As you can see also, aircraft in poor weather conditions, essentially. It actually works. You can automatically detect what type of aircraft it is. This is a company which uses SAR imagery, and this is an example from an airport in Thailand, and it shows how the algorithms are able to detect aircraft, and they can also basically classify the type of activity they're performing. So having this capability means that it's possible to detect and monitor force massing and force maneuvers of the adversary, and it's also possible to count and locate the number of tanks, artillery, and aircraft, of course. So having this capability and monitoring one side doesn't give you much, but if you do it over a longer period of time and at a number of sites, it highlights pattern of life, and it provides early warning in the change of the intent and activity of the adversary. So that was the technology. This is how this part of the presentation will speak about how this may affect the relationship of nuclear weapon states and nuclear stability. Well, nuclear stability is defined as there being no advantage in striking first, and the fear of the adversary striking first is also minimized. So when we have lack of information and predictability, this increases the danger of a nuclear war, either from an accident or misjudgment. It leads to worst-case scenarios, such as I described during the Cold War, where it's safest to assume that the other side is always deploying new weapons, deploying forces, and preparing to strike. And because of this fear of a surprise attack, even if neither side wants a war, there are great incentives to actually strike first. So opacity, ambiguity, lack of information will decrease nuclear stability. On the other hand, removing the fog of war, providing more predictability, will minimize guessing in worst-case scenarios, and will decrease the probability of decision-making based on incorrect information or fear. So transparency in this context will increase nuclear stability. States will be incentivized to attempt to obtain some capability if this can be observed early enough to prepare and react. It will also close the gap between the perceived intent of the other side and their actual capabilities, and it will enable clearer communication, making it easier to recognize peaceful intentions, if there are any. In the context of nuclear weapons, overhead transparency provides nuclear monitoring. So it provides a better picture of the adversary development, and it also can be used as a confidence-building measure, as a state can expose their activity to show that they have peaceful intention, as I mentioned before. So imaging satellites can be used to detect construction and monitoring of nuclear activity. The example being, of course, detection of the Chinese missile silos. It can also be used for monitoring of facility operation to a degree, using either infrared imagery or even using optical imagery to monitor the number of vehicles entering and leaving the site, from which one can infer staff demand, material demand, and even production. Kind of breaking up. I'm moving too much more. Anyway, it can also, imagery can also be used to geolocate air bases, military facilities, nuclear facilities, to observe signatures such as supply chain activity, such as parking activity, such as training activity. All this gives you an indication on the level of activity of a nuclear facility and or a military facility in general. With real-time observation, it may become possible to immediately discover and classify vehicles, artillery, aircraft, ships, and so on, as soon as they appear anywhere, using, of course, AI. Okay, so imagery is also useful for arms control as a verification mechanism, because states can demonstrate commitment to obligations they assumed, and they can also unilaterally demonstrate that they are not doing something wrong. But it's easy to assume as a scientist and fall into a trap thinking that there is this perfect verification mechanism. There is an equation which, once discovered, will mean that both sides will see the truth in it, and we just hold hands and agree to a treaty. It's easy to assume as a scientist that these things are governed by logic and rationality, when in fact they're governed by other mechanisms. So arms control can, if you look at New START, for example, if you read it actually, it's very easy to cheat. Essentially, both sides pretend to verify and to be verified. When one side decides not to pretend anymore, they just stop pretending, as Russia is doing right now. So arms control can be understood as a method of communication, as a way to minimize guessing in worst-case scenarios. It's not foolproof. And seeing the adversary helps. So with satellite imagery, it's not possible to observe everything. You cannot see behind walls and underwater. And that's a good thing, because it means you will not disclose sensitive information. You cannot see a chemical composition of a warhead or how it was composed. You can, as such, it's easier early step to a more comprehensive regime. And while the initial probability of detection is low, it's kind of a big data problem. You can fuse different types of information over a longer period of time, which includes not only imagery, but also social media activity, human intelligence, official statements, and so on. With time, uncertainty is reduced and trust between parties is augmented. In more practical terms, it makes deception more difficult in the long run. It makes initial assessment of forces and capabilities more accurate, which means it's also easier to negotiate new treaties. It allows for an easier demonstration of compliance, as I've talked about before. So New START is the last remaining treaty which limits the size and composition of nuclear forces. It's expiring next year, and it's unlikely a new equivalently intrusive treaty will be agreed on. So overhead imagery can replace some of the on-site inspections. For example, it becomes possible to monitor uploading of missiles, as shown here. The inspected party can also open silo doors, hatches of submarines, and the inspector can then check if there are any missiles inside and how many. You could place IDs on bombers, so the inspector can, at any point in time, can localize and count these bombers. So there are many ways how this new technology can replace legacy, more intrusive inspection verification procedures. And in case there is no arms control, If arms control can be understood as a form of communication, satellites provide a permanent layer of transparency and essentially provide a channel of communication even if there's nothing else. So no side is left in the dark. So those were the good things. There are also the bad things, of course, things which will cause nuclear instability, if you can call it like that. Of course, with overhead imagery, it becomes possible to prepare attack. It also reveals disbalances between sides, so the stronger side can take advantage and attack. The weaker side can preemptively attack, or it can just cause a nuclear arms race. Remote sensor data is always partial information. You can see something is happening, but not know why. It usually confirms biases rather than challenges them. When using algorithms, they're often black boxes, and it's very difficult to verify all the conclusions at the speed of decision making. Commercial imagery has benefits and also has disadvantages. Having more eyes on what's happening may disincentivize aggressive activity. It may also help check conclusions, but it also makes it difficult, the crisis management. So the classical example is the Cuban Missile Crisis, and what would happen if the missiles on China, on Cuba were revealed on social media, and everyone was stuck in their own bubble of information discussing this. There would be no way for a secret deal which ended the Cuban Missile Crisis. It may have ended differently. So nuclear deterrence relies on survivability of retaliatory nuclear forces. They need to survive the first strike and then be able to retaliate. And development of any capability which threatens these forces or is perceived as such, in theory, erodes nuclear deterrence. So nuclear weapon states, to make their weapons more survivable, they employ opacity and ambiguity in deploying and developing their weapons. They make more weapons than they need. They harden their assets by placing them under shelters, underground, underwater. They make them mobile, they conceal them, they diversify the number of ways these weapons are delivered, and so on. The most survivable methods to deploy are considered to be mobile launchers, as shown here on the top left, and ballistic missile submarines. While new technology does not particularly threaten submarines, they are not increasingly more visible, and as Lindsay showed, quantum sensing also does not affect them. This is not the case for mobile missile launchers, which are employed by China and Russia. Overhead transparency means they're more likely to be detected and tracked, which may also be the reason why China is deploying these clusters of silos recently. So with persistent multi-angle band monitoring and years of observation, the seeker can reduce the uncertainty on the location of these launchers, and then it kind of becomes possible to attack them. But it's worth knowing that you need more than one warhead per launcher, and the attacker would also need at the same time to destroy submarines, bombers, and silos. So, for example, the US does not have enough warheads to even attempt that. And even if they did, there is a large probability that some of the forces would survive and strike back. So the conclusion here, even if it becomes possible to see them, it does not become rational to actually try to attack them. It does not become suddenly irrational to start a nuclear war. Lack of parity does not default to an all-out nuclear war, as historical examples show. So this slide just goes over what I talked about, and I see formatting is messed up. Anyway, leaders, so my conclusions are, leaders are humans. Humans are irrational and dangerous when afraid and lacking information. Overhead transparency provides more predictability to their relationship, could reduce the nuclear danger, and facilitate a new generation of arms control. Increased transparency can also invite conflict and can introduce new dangers. So transparency can enhance the deterrence, or it can be abused and weaken it. It just depends how states approach it. It may soon become possible to localize launchers, but that does not mean their effectiveness as a retaliatory force is eroded. It still remains irrational to attempt to destroy a fleet of TELs. So going back to the beginning, greatest danger of a nuclear war is from miscommunication and miscalculation, and transparency will increase nuclear stability. And I conclude. Arms reduction was made possible by a change in political relationships, and arms control was facilitated by technology. In the future, which may be driven by technological change, but possibly without effective arms control treaties, states face dangerous challenges. they can counter evolving transparency by even more secrecy, which will further fuel worst-case projections. And they can pursue also enlargement and diversification of their weapons and delivery vehicles. And this will start a nuclear arms race. An alternative is to accept that rational leaders do not start nuclear wars, that the greatest danger of a nuclear war is miscalculation or miscommunication, and to choose to establish norms of behavior where transparency does not fuel instability and instigate a nuclear arms race, but limits racing and reduces the probability of escalation. And I end with this: the nuclear danger was started in secrecy. It can only end with full transparency and in plain sight. Thank you.
We have time for a couple quick questions. If not, we'll move on to our final speaker of the session. Thank you very much, Igor.
Sorry.
All right, so our third and final speaker today, and apologies again for the microphone issues here, is Professor Curtis Asplund from San Jose. So Curtis's physics research is focused on theoretical high-energy physics, particularly quantum aspects of black holes. He earned a bachelor's degree in math and physics with a minor in philosophy from Oberlin and a PhD in physics from UC Santa Barbara, and then completed postdocs at Leuven and Columbia University. Professor Asplund was a high school teacher for several years near Washington, D.C. before becoming a visiting faculty member at Franklin and Marshall College. He's currently assistant professor of physics and astronomy at San Jose State and a Public Voices Fellow with the Op-Ed Project. And his teaching, in addition to physics, includes a focus on ethics, public policy, and the role of scientists in society, especially in nuclear issues. And in 2022, Professor Asplund studied nuclear weapons policy as a next-generation fellow with the Physicists Coalition for Nuclear Threat Reduction. So please help me in welcoming him.
Cool. Yeah, sorry. It's just... Hello. Hello. Testing. Sounds good? Okay. Thanks, everyone. Appreciate your patience with all of that. And thanks for your attendance today here at this session. Okay, so I'm going to be less technical in this talk, give more of an overview of the meeting that inspired this whole session. Okay, since I'll be talking about some policy and political things, I just added this disclaimer. The views expressed here are my own. I am a public employee of San Jose State University and ultimately of the state of California. So these views are my own personal views. Okay, a few other things to mention at the outset. Just a bit about me personally. I am a US citizen from Southern California. I'm happy to be here in Sacramento, of mixed heritage from Mexican American and Swedish Lithuanian American. As Dylan mentioned, I'm a theoretical high energy physicist mainly. That's my background and training and my main research area. And I also teach this course on physics and public policy at San Jose State, and I bring all of these identities to this work. I want to thank a few different people and organizations, the APS overall and the FPS in particular, the Forum on Physics and Society. Fred Lamb was one of the instigators of this and was going to be the chair, but Dylan is doing a great job, so I want to thank Dylan Spalding as well. and the support and mentorship of the Physicists Coalition for Nuclear Threat Reduction. I'll say more about that later. And the Princeton Program on Science and Global Security, which has also provided me some support with regard to these issues over the years. In addition, the meeting that I'm going to talk about, the ICTP meeting that had a whole organizing team, Stuart Prager, Frank von Hippel, Zia Meehan, Jürgen Altman, and Gates Neuneck were all part of that, so I want to thank them. I also want to do a land acknowledgement. So we acknowledge the land currently occupied by Sacramento City, here where we stand. It is the traditional home of the Maidu, Miwok, and Nishinan people. These sovereign people have been caretakers of the area since time immemorial. Despite centuries of genocide and occupation, the Maidu, Miwok, and Nishinan people continue as vibrant and resilient, federally recognized and unrecognized tribes, band, and rancherias. Today, we honor and recognize our Maidu, Miwok, and Nishinan tribal neighbors for their contributions as the caretakers of the Sacramento Valley and honor their sustained existence. And I'll also acknowledge that this was adapted from the Sacramento City College land acknowledgement. Okay, I want to spend a little time justifying myself, I suppose, and this whole session, and in some broader sense, the Forum on Physics and Society, which I believe has an important mission. It may, or I may or may not be preaching to the choir about this since you are attending this session, but just to say a few words of background here, it could be asked, and it often is sometimes among physicists, whether we should be talking about these issues as well as how we should be talking about them. And I offer a few works that discuss this issue in interesting ways. So the first I'll mention is a book by a philosopher of science, Heather E. Douglas. She talks about the value-free ideal, which is her, a way of talking about scientists very narrowly, as though the ideal of their work was to be free of all human values and just to be completely concerned with facts about the natural world. But she really challenges that as an ideal for actual scientists in this world, and I think does so quite persuasively. Instead, there are various other kinds of models for how scientists can be in the world. Sometimes they're called honest brokers or issue advocates. Those are terms used by Pilke in his 2007 book, The Honest Broker. Sometimes people talk about citizen scientists. There's a nice collection of works by Frank von Hippel and others in that book, Citizen Scientist. And I think in this context, it's also important to mention the work Merchants of Doubt by Naomi Oreskes and Eric Conway, where they look in quite critical detail at several specific physicists who have been active in policy circles over many decades and show some of the perils as well as the opportunities for that kind of engagement in the public sphere. So in particular, they are concerned with several physicists who were climate change deniers, who denied problems with the ozone layer, who cast doubt on the causal link between cigarette smoking and cancer, and so on, quite a few different examples, as well as physicists who, on the other hand, were actively concerned with the dangers of climate change and pushing for policy change around it, for example. So I highly recommend that book for all physicists to read in particular, as well as others. Okay, and of course there's a long history of physicists in particular who have been active, particularly on the nuclear weapons issue. And I won't try to summarize that history. There are several very good works on that kind of history. I'll just mention one recent article that came out in March 2024, this year, by Frank von Hippel. It's in the Bulletin of the Atomic Scientists, and it goes through a number of important figures in this history. One in particular worth special mention here is Joseph Rotblat. He was a member of the Manhattan Project, but left it on ethical grounds and then was later active in international organizing around nuclear disarmament and discussing the dangers of nuclear weapons internationally, and was part of those circles for many decades. And then someone who doesn't get mentioned in that article, and I think deserves a bit more attention in our collective history, is Lise Meitner, who was one of the discoverers of nuclear fission and was part of that circle of physicists in the early 20th century in those days, but who scrupulously refused to work on nuclear weapons, even though she was all too aware of the dangers of, for example, Nazi Germany. She had to flee, probably for her life because she was Jewish, and was very aware of the dangers, but nonetheless was very clear on her ethical stance that she would not work on weapons, and maintained that stance throughout her life. Okay, moving closer to today, a number of physicists have argued for re-engagement with these issues. So I'll just mention a few articles on the left side. 2015, there's an article by Zia Mian about advocating for scientist engagement. More recently, in 2023, Stuart Prager and Frank von Hippel wrote an article arguing that physicists need to be talking about these issues urgently. I'll even, if you'll allow me, mention my own op-ed that came out some weeks ago in the wake of attention around the Oppenheimer film that discussed these issues and advocated for engagement. And then I'll have a few quotations here. First from Stuart Prager: "We are moving backwards into a dangerous future right now. It is a critical time for physicists to re-engage in the problem." And then another quotation by Karen Hallberg: "The world is currently in a very difficult situation with escalating wars involving countries that have nuclear weapons." Okay, and indeed, the dangers from nuclear weapons are very much real and present. Here is a quick look at stockpiles among the nuclear-armed nations of the world. And in fact, most of these nations are not just maintaining these stockpiles, but they are building new weapons and actively engaged in research and technology, as well as deployment, testing of new weapons. So as dangerous as this picture is, even if it were static, it is getting worse. Okay, so I can't go into a comprehensive picture of the increasing threats from nuclear weapons, so I just grabbed a few headlines from generally like the last week or month. It's not hard, sadly, to find headlines about nuclear weapons threats in the world on any given week or month. So in particular, in Russia, there is a lot of scary rhetoric coming out, as well as tangible moves like the movement of weapons into Belarus. In North Korea, there is a drumbeat of testing of missiles, and there's a lot of thought that there will be additional explosive nuclear tests as well. So yeah, I'll just, random kind of collection of articles. And then there is a interesting set of opinion pieces by the editorial board at the Washington Post from late last year, which just laid it out very clearly in that headline, that it just is a new nuclear arms race. And so though the Cold War is long over and we maybe thought or hoped that those days were behind us, we need to face the reality of a new nuclear arms race and think hard about how to slow it down. Okay, at least that's the opinion of the editorial board. Okay, in the international context, I just want to do a little sample of sort of ethical thinking about these issues. This is the kind of thing I talk about in my course, for example. I acknowledge that this is just a surface level sort of first pass ethical analysis, but nonetheless, I think it illustrates some important points. I find this concept helpful sometimes. This philosopher, Wolff, moral philosopher, calls it the risk triangle, but it's just a way of configuring different parties in a moral or ethical situation. And I'll just draw your attention to row 3 there. That's the moral hazard row, whereby in that situation, there is a decision maker, party A. That party also happens to be the one for whom the benefits are afforded or allocated. And then there's another party B who has to pay the costs. It's oversimplified perhaps, but is a kind of basic configuration that can occur in certain public policy settings. And I mention it here because it's relevant in an international context where most nations do not have nuclear weapons. So non-nuclear armed nations, however, do have to pay costs and bear risks of nuclear weapons in many cases, although they have little to no say over the policies around them. So they typically don't have to directly pay for the weapons themselves, but they may have to pay costs of, for example, remediating nuclear fallout from nuclear testing throughout the 20th century, for example. And importantly, they bear the risks of any nuclear war were to break out. Many non-nuclear countries would also be harmed in such a situation. So, and then more generally, many people, like, most of us sitting in this room don't have much say over nuclear weapons policy, but many of us would be affected if there was a nuclear war. And if those of us who are US taxpayers do pay for the nuclear weapons. Okay, so on the other hand, the US has a special situation where we can influence policy, at least in principle, because we have certain political rights in this country. In other countries, citizens have many fewer rights to speak out or to influence their government. So the moral hazard there is more acute, I would argue. Okay, so just to kind of pile on the bad news for a while, we will get to more hopeful content in a little bit. Okay, so the situation of nuclear risks is increasing in complexity for several reasons. So one persistent risk that always has been there with nuclear weapons is the risk of just unpredictable or unhinged leadership. And that's particularly troubling in cases, which is true in most countries where the head of state has the singular control over those weapons. So that's true in the United States. The President of the United States has sole authority over the weapons, and but that's true in general. So in most nuclear armed countries. So that risk has always been there, but there are other factors to consider as well. So I just listed a few here. Even in the case of an unintentional kind of nuclear disaster or war, we have different factors like just regular old human error. A human makes a mistake in an assessment or in the procedure. And now, of course, we do and will have to increasingly worry about AI type of errors. In addition to that, we might worry about acts of terrorism, cyber attacks, software or hardware failures, misunderstandings, or other forms of accident. This is not a comprehensive list, nor is this a list of mutually exclusive categories. These are all, can potentially overlap with each other. And there have been many close calls. There's an excellent book by Schlosser from 2013 that goes through some of them in quite a bit of detail, and there's more research on that as well. In 2023, there was a very significant study done by the National Academy of Sciences, which was trying to take this set of concepts very seriously and apply modern risk analysis techniques to it. So I do encourage you to take a look at that if you're interested in this topic. For now, I'll just leave it at a quotation here at the end that the report, one of the main conclusions of the report is that the risks of nuclear war remain real and are becoming more complex as new technologies and new adversaries arise. Okay, and then I will just acknowledge that it's hard to quantify any of these risk factors, but the committee, the report was certainly clear that they are real and becoming more complex. All right, so given all of that scary stuff, it served as kind of motivation for a group of physicists to come together and see what we can do about this. And so I like this group photo of us, which included my co-speakers, Igor and Lindsay were also there. And this convened in October in Trieste, Italy, at the International Center for Theoretical Physics. And there were a number of sponsors of this meeting. And let me tell you a little bit about the meeting, which included some of the, as a main component, some of the technical material that the previous speakers have already covered. But in addition to that, I wanted to show you a few other things. Okay, so, and in fact, as our chair Dylan already mentioned, the meeting was about 45 physicists from about 15 nations. And we had a few themes, as I mentioned, technical talks about new technologies and new developments. Then we went a bit into the history and state of physicist engagement and advocacy, which I've already alluded to a bit as well myself. Ethical questions about weapons-related work, how to communicate to the public and students, and then ultimately how to organize national, international, and local efforts to advocate for policy change. Okay, so let me just give you one further example of a technical area of research that was not already covered. So this is about impacts of nuclear war. It is true that any nuclear war will impact many nations. They are inherently hard to contain types of events and conflicts. And there is ongoing research about this. There was, of course, some of this going back to the early days of the Cold War, but there was serious limitations to that kind of research, and it's in need of updating. And so to give you an example, we heard from Dr. Alan Robach, who is a longtime researcher on climatic impacts and on the phenomenon of nuclear winter. And some of his latest work, he and his collaborators, are about the consequences of nuclear winter on food systems. So nuclear winter, in a nutshell, is the phenomenon where nuclear blasts inject especially soot and other dark molecules and suspensions high up into the atmosphere, into the stratosphere, which can then migrate over large distances and persist in the upper atmosphere for many months or even years. That causes a reduction in the amount of sunlight that reaches the ground, and it is no surprise then that that will affect agriculture. And that is one of the most damaging kinds of effects because, of course, as humans, we depend on agriculture to feed ourselves. So that leads to this kind of concept of a nuclear famine that will have even more effects than previously understood, more casualties. So in the studies that they've carried out, a nuclear war between India and Pakistan, for example, in their models leads to the deaths of over 2 billion people, which includes many people outside of India and Pakistan. So there's a whole population of people throughout Asia that especially would be affected, and there would be some effects even beyond Asia. A nuclear war between the US and Russia would be even worse, and in their models caused the death of over 5 billion people. Again, a lot of these deaths are through nutritional deficits, essentially famine, starvation. Okay, so this is an ongoing area of research that should probably impact the way we think about our nuclear weapons policies. And we heard about it at this meeting, and we discussed it, and it's one of the ways that in this case, climate scientists, meteorologists, climate physicists are making important, significant discoveries about the effects of nuclear war, using modern research methods. Okay, I think this area of research is really interesting, so interesting that I also have a whole poster about it. So another US National Academies of Sciences report is coming out soon. It's about the potential environmental effects of nuclear war. And it was mandated by Congress in 2021. And I think this is a really interesting way that physics or science more broadly is influencing nuclear policy, through the vehicle of the national academies in this case. So yeah, if you'd be interested in talking about this with my student, Emily Foreman, who's over here, please stop by our poster on Friday. I think it's at the 2 p.m. poster session. Okay, another main thing we did at this meeting was just hear about nuclear policy and advocacy in various nations. So among the nations represented, I have this list here: China, Russia, India, Pakistan. So those are all nuclear weapon states, as well, France, UK as well. But then there were quite a few non-nuclear weapon states as well: the UAE, Japan, Italy, Germany, Argentina, Brazil. And we heard about some of the challenges faced in these nations. So in some of these nations, there are varying degrees of restriction on freedom of expression and political advocacy. In some cases, it's quite extreme. They're, very extreme restrictions. In other countries, it's not so extreme. There's a whole spectrum. And then similarly, there's a spectrum of existing organization and infrastructure for physicists to engage in any kind of political advocacy around this issue, nuclear weapons threats. Okay, so of course, these can also be framed, well, at least in some cases, as opportunities. So there is, room to grow here. There is the possibility for grassroots organizing in a lot of different countries around the world. And this can strengthen the case by having a, potentially strengthen our efforts and our network through these international connections. And I think at a deeper level, I didn't put it on the slide here, but at a deeper level, one of the outcomes of this meeting is just to cultivate a global sense of connection, a global conscience that is based on human rights and our common human identity, that's not based on national interest. And so that is really important, I think, and that was the spirit of this meeting. Okay, so we are at the American Physical Society, so it's relevant to talk about the United States, and I want to emphasize that here in the US we have some unique circumstances. In particular, relatively high degree of freedom of speech and expression, the right to petition our government, and congressional representatives that, again, or at some level actually do listen to their constituents and listen to expert opinions. I have actually successfully talked to congressional staff and had them listen and seen some influence occur at the policy level, So that's not to be taken for granted. Many other nations, there's nothing even close to that. And of course, in some nations, there is something in between. Okay, we also, of course, have one of the largest nuclear arsenals in the world. So, there's a responsibility there. And we have some existing organization and infrastructure, in particular, the Physicists Coalition for Nuclear Threat Reduction, that is already in existence, and we would love for you to think about joining and finding common cause with. So I'm actually going to put that up, but I'm going to leave that up at the end, so I'll just move on for now. In terms of the U.S., right, we have a couple of, there's things to be aware of in the United States. Okay, first of all, we are legally obligated under the Non-Proliferation Treaty, the Nuclear Non-Proliferation Treaty. And we also, at the top levels, speak about our commitment towards nuclear disarmament. So it's not like there's any debate about that at the formal level. We are obligated to this under, and I'll emphasize the Non-Proliferation Treaty that comes from the late 1960s. That is a Congress-ratified, presidentially signed international treaty that is binding on the United States. And it says in it that we must pursue, at an early date, negotiations towards nuclear disarmament. So, that's the deal, but in practice, that is not how it's been playing out. In fact, so there was some disarmament in the 1980s and 90s especially, but in the last 20 years or so, there has been very little of that, and on the other hand, there's active maintenance of our arsenal, as well as developing a whole slate of new nuclear weapons and associated technologies. So there's a great series done by Scientific American. It just came out last year, some months ago, and it has a whole series of articles about the new nuclear age, and the series of articles argues that the US is beginning this ambitious, controversial reinvention of nuclear arsenal with incalculable costs and unfathomable risks. So it's really emphasizing costs and risks of this policy and arguing for those. I'll just point to a couple of articles here. Like in the middle, for example, it talks in detail about the fact that many ICBMs are located on or near Native American reservations without the consent or sometimes even the knowledge of the Native people who still reside there. And that takes us back to the moral hazard kind of situation. So I really recommend consideration of that issue. And then on the lower right there, Philippe, a colleague of mine, has some really interesting new research on the impacts of, say, a nuclear war that involved our ICBM silos. So that's really important. I know I'm running out of time, so I'm trying to wrap up here. One last topic that occurred at the ICTP meeting was talk about physics education and incorporating ethics into our curricula. I'll just say that this is in development. I'm very interested in this as a physics teacher myself, and I'll point to some excellent work by a couple of my colleagues, including Brianne Gutman, who is a professor at San Jose State, on physics education research about best practices for teaching that in the classroom. So I think it's a really interesting area of physics education research. But this is ongoing. I'd be happy to talk to you about it if you're interested. Okay, so the next steps are, just continuing this kind of work. There is a kind of primordial international working group that is in formation. We're working on it, and we'd be interested if you're interested in that, please let me know, or you can kind of work through the coalition. But basically, we're trying to keep this going and keep connected. So thank you for your attention, and I'll just leave this up here. We'd be happy for your interest and engagement with this issue. There's the website and a QR code to sign up with the coalition and learn more about these kinds of issues. Okay, thank you very much.
All right, we have time for a few questions.
Yes. How do you get people from some of these countries like Russia, China, North Korea, maybe Iran, involved in this? I mean, could they be in danger for being involved in such an effort? What do you saw? Some of them were at the meeting. What do they say about that? How do they deal with that?
Yeah. No. Thank you so much for the question. And indeed, it could be dangerous. Some of these regimes are quite harsh on. So in practice, it may not be possible for some of the countries you mentioned for there to be any real organizing within those countries, and we acknowledge that. Some other countries, there is a kind of middle ground where scientists may be allowed to do some kinds of research, make some kinds of statements, as long as they are not directly critical of the government policy. They can just sort of make statements that seem policy neutral. That seems to be okay enough in some cases. But the reality is that it is dangerous, and for some countries, for nationals of some countries, and that is an unfortunate reality for now. I think the general mood was, let's just build trust if we can. Let's build relationships, and that may be the best we can do under the current political climate. Hope for better times ahead. Yeah. Okay. Other questions?
Yeah, well, thank you. This is extremely important, of course. One question I have is about the danger of the authority of a leader, one leader, to push a button and start a chain reaction. So how much do we know? I know nothing about this policy. Is it possible for a leader of USA or Russia to decide themselves to do that? Or can one build around that leader a mechanism whereby it's impossible for any one leader to make that decision?
Yeah, thank you for that question. And I will say, I don't have a comprehensive knowledge of the answer to that question, especially in other countries. It's not clear to me, actually, the answer to that in most other countries. What I do know about the United States is that the president has this kind of formal sole authority over whether the weapons will be used. He does have to go through a chain of command, so there are military personnel involved, but there is no congressional review or expert panel that has to weigh in necessarily. He's supposed to consult with advisors, scientific advisors, but ultimately it's the president's decision, and the people under him are obligated to obey. Now there's some wiggle room that I've heard about, well, if it's an illegal order, maybe they don't have to obey, but it's a kind of slender reed to hope, to hang our hopes on that some, general Air Force officer will disobey the president because, they have a moment of conscience. So I certainly think in the US we should change that policy. It should not be sole presidential authority. There should be a system, with multiple people involved who have to consent. And I think we should advocate for that. I think there is some political scope for that to be changed in Congress, and I think Congress has the authority. So, that would be my personal opinion. Yeah. But I hope that answers your question. Let me get the person at the mic. Sorry, we can talk in there. Oh, do you want to follow up?
Microphone.
Can you speak into the phone?
Can you please use the microphone?
If you want a direct follow-up?
It is a comment specific on your last comment.
Mm-hmm.
The point is that I think that both in the States and in Soviet Union, in the former Soviet Union, there is at least 2 or 3 people must contribute personally.
Mm-hmm.
So it is not just sufficient. The point is, in my view, much more dangerous in some other countries like Pakistan, for example, or Iraq, where the structure of the power is more complicated.
Okay. Okay. Thank you for that comment. Thanks.
So what is the argument to, because it seems like in the U.S. And any nuclear power, deterrence is the key. Like you worry someone won't shoot you because you can shoot them.
Mm-hmm.
What is the argument for total dearmament that you use to address people who say they're worried about deterrence, either against no nuclear powers or against some rogue power rising in the future, the nuclear weapons, and you don't have a deterrent? What is the besides good faith and hope and humanity? What's the argument?
Okay, if I think I understood your question, nuclear deterrence is sort of the mainstream strategy. I would just emphasize that because of all of these things here, it's not like that is not a safe stalemate. That is a positive risk for any one of these things to then result in a nuclear disaster. So, even if you think strategic deterrence is like good geopolitical strategy, you can't do that forever. Any non-zero risk means eventually it's going to go bad. And in any case as well, we are legally obligated to work towards nuclear disarmament under the Non-Proliferation Treaty. So we've already committed to that. So, the point of view is, let's just do that.
Follow-up question to this point exactly. Can one rationally understand what is the motivation to now build up even more nuclear weapons? Don't, for example, especially in democratic countries where I think governments are more rational and say, why spending this money? We have enough to retaliate with the annihilation of whoever attacks first. So why spending extra money and make more weapons? I mean, where's the sense? We have enough already, don't we?
Great question. Yeah, I don't want to try and even answer because I don't think it's my position to make the argument of the other side. Of course, there are people who will make an argument against what you're saying. I'm not one of them, so I'll just leave your question as a very good one.
You don't have an explanation of the other side? What is their argument?
I mean, they certainly do have statements that they make based on national interest, then their theory of national security, their theory of political power and strength and projection of strength. There's many kinds of words and concepts that float into those statements, but I won't try to put them into a rational framework because I'm skeptical that it can be.
I guess I would add that there are arguments now that, contrary to the Cold War, when the U.S. was primarily thinking of just countering Russia, there's a lot of rhetoric now that we need to be prepared to counter Russia and China even simultaneously. So there's a very different way of thinking, right, that changes the strategic posture and the planning for scenarios like that, whether you think that's a good idea or not. And that points to some of what Igor showed with the photos of the Chinese missile silos, things that's raised considerable alarm, particularly in Washington. All right, if there are no further questions, I'll remind you, if you enjoyed this session, please consider coming Friday morning to session L04, where we'll continue talking about the role of physicists and arms control, past and future, as a panel discussion. The Forum on Physics and Society has a table now at the back of the room, which we would love for you to visit. And thank you again. Let's thank all three of our speakers one last time.